All right, how's it going? Welcome back to another video here in the series on vector calculus. We are still on this section here on surfaces and surface integrals, and we've been working through this section for a little while now, right? And the picture that we've been working with up until this point has kind of looked like this, where if we have a 2D plane, in other words, we're working in R2, then the domain that we're integrating over D is going to be some subset of R2, right? And up until this point, we've done a lot with just this picture. We've talked about how we can, just integrate over this surface, but we've also talked about how we can transform coordinates, maybe from the XY Cartesian coordinate system to some new coordinate system, and then how to perform surface integrals in that new coordinate system. And then in the most recent video, we also talked about how we can generalize this picture, or some ways which we can generalize this picture, right? We talked about how we can work with 3D volume integrals, how we can work with n-dimensional integrals, and how we can integrate over vector-related quantities, whether it's a vector function or a vector field, right? So it might seem like we've done just about everything that we can with surface integrals. But there's been one sort of implicit assumption that we've been making up until this point, and we haven't talked about it too much because it hasn't really been necessary to talk about this assumption. But the assumption is that whenever we've been performing an integral over the past 3 videos, the dimension of the domain D always matched the dimension of the overall vector space that we're working in. And here's what I mean. In this XY plane that we have right here, the dimension of our overall vector space, R2, is a 2-dimensional vector space, right? And then in turn, the domain D that we're working with is also a 2D space itself. It can be parameterized by 2 different variables. And then even in the larger dimensional integrals, when we worked with a 3D integral or an n-dimensional integral, the domain in the 3-dimensional case was it could be parameterized by 3 variables. It was a volume integral. And then the same thing with the n-dimensional space. D in that case would have been an n-dimensional volume parameterized by n different variables. So there's always this implicit idea where the dimension of our domain matched the dimension of our vector space. But there are a lot of instances where that will not be the case. And that is kind of supposed to be this picture right here. So what I have here is I have sort of this overall cube looking thing, which is supposed to represent R3. In principle, this could be any vector space great with a dimension of 3 or larger, but I just chose 3 because that's kind of intuitive, right? We can kind of visualize a 3D looking cube right here. And then embedded within this 3D cube is a surface S. Now this surface is still a 2-dimensional surface, but it lives within a 3-dimensional space. So we can think of this surface here as an embedded surface. And it is now in this picture where the dimension of the surface does not match the dimension of the overall vector space, whether this is R3, R4, R10, or Rn. The dimensions are inherently different. So what we're going to be working with going forwards is ultimately how can we integrate over these embedded surfaces right here. Now, I should mention before we get into anything, for the purposes of this video series, we can think of an embedded surface as some surface S contained within an overall larger space. And for the purpose of this video series, that is an accurate way of thinking of an embedded surface. But I should mention that in math, an embedded surface has this precise definition where it talks about a surface which does not have any self-intersections within it. And in case you're wondering, like, okay, well, what would be an example of a surface which does have self-intersections and hence is not considered an embedded surface? Some common examples are the Klein bottle, Whitney's umbrella. There's a type of surface known as the Roman surface, which has even more self-intersections compared to another type of surface called the Boy's surface, B-O-Y' surface. So these are all just some examples of surfaces with self-intersections. And essentially we're saying that whatever type of surface that we're going to be integrating over, it's not going to be in kind of that class of these surfaces that do have self-intersections. I would recommend just looking up what those surfaces more or less look like if you just Google them, because they're really interesting to look at. It's just that for what we're going to be doing, that we're not going to be dealing with those types of surfaces. Okay. So hopefully that makes sense, that now we're going to be working with a surface within an overall larger space with the ultimate goal of being, how do we integrate over this type of surface right here. Okay. So hopefully that makes sense. Now, the first step in even being able to do that is we're going to want to be able to parameterize this surface. We want to be able to write it in terms of two variables, which we can, I guess, generally call u and v, such that we can ultimately integrate over u and integrate over v to get the overall value of whatever surface integral we're computing. Okay. Now, we might be thinking, when we hear that we might be saying, well, don't we already know how to do that? Haven't we done that over here? And the answer is, well, yeah, we've worked with that over here. We've talked about how we can parameterize a subset of R2 in any coordinate system. But what we're going to see pretty quickly is that when we start to work with these embedded surfaces, that there's a little bit of additional non-trivial information that's needed in order to properly parameterize the surface. And because of that, that's going to be kind of the main goal of this video. It's just to say, how can we even parameterize these before we actually start to integrate over these quantities? Okay. So hopefully that makes sense. Now, what I want to do to start off is to kind of just say, well, why is this idea of parameterizing S? Why is it a non-trivial process? In other words, why can't we just use our knowledge from here and just immediately translate that over to here without having any issues? And what we're going to see is that with maybe an initial attempt to be able to parameterize an embedded surface, we're going to quickly run into some issues. So I want to bring those to light before we really go about parameterizing this as a first step. Okay, so I drew out I attempted to draw out at least this overall cube, which is supposed to represent R3, and the specific surface that I'm working with is going to be this spherical shell right here. So when I say a spherical shell, this object right here is not a solid sphere, but it's rather a hollow sphere. So we're only considering the outermost radius of this sphere, and that's going to act as our surface. Okay. And what we could do, I guess, sort of in a naive approach, is if we wanted to say, okay, well, let's kind of parameterize this type of surface, and we didn't know a whole lot about parameterizing surfaces, this might be a first step that we would take. And we might say, okay, well, maybe let me just write out the equation of a sphere, because I know how to do the equation of a sphere. I've hopefully seen that out at one point in one of my algebra or geometry classes, right? And for the equation of a sphere that has a center, so if this spherical shell right here has a center of x naught, y naught, z naught, and it has a radius of r, then we could say that we know the equation of a sphere is going to be x minus x naught squared plus y minus y naught, so y minus y naught squared plus z minus z naught squared equals r squared. Okay. And that might be a first step that we would do. So we'd say, okay, well, let's maybe write out the equation of a sphere and see what we can do with that. Let's make that a little bit cleaner. Now, hopefully you could immediately see the issue with parameterizing the sphere by writing it out this way here, because right now this equation has three different variables in it. It has x, y, and z, even though x naught, y naught, z naught, and r are all constants. And the issue is that if we ultimately want to parameterize any surface, which in this case is a spherical shell, then we're going to want to be able to express this surface in terms of only two coordinates as opposed to three, right? Now, I should mention that the spherical shell is kind of an exception to the overall approach, because we actually know a very convenient coordinate system for working in, when dealing with spheres, which is spherical coordinates. And in spherical coordinates, our three variables are r, theta, and phi, right? And it looks like we have three coordinates here as well, but if we're working with a spherical shell that has a constant radius uppercase r, then this radial coordinate gets fixed to uppercase r, and then our remaining two coordinates are theta and phi. So you could easily just make the argument, and you might be thinking this while watching the video, well, yeah, I already know how to parameterize a sphere by using spherical coordinates, right, theta and phi. So what's the big deal, right? And the idea is that this was very convenient because of the shape that we happen to draw on the board. The only reason, I should say, why I drew a sphere on the board is so we could write out a clear expression for the equation of a sphere here. But let's suppose that maybe our surface was not a spherical shell, but just some arbitrary surface. That arbitrary embedded surface should be also represented by two different coordinates. But this approach, by starting to write out the equation of whatever that surface is, just isn't going to be overall that useful. Because in the general case, this equation will have a left-hand side where you're going to have some function. It might not be this function, but it's going to be some function of x, y, and z, of your three Cartesian coordinates. Or more compactly, it's going to be some function of just r, right? And on the right-hand side, you're going to have some constant, which I can just call c. So what I'm trying to say is that whatever surface that you're working with, if your first step was to write out the equation of that surface, let's say you find the equation of the surface and you were to write it out, you would inherently be writing out a scalar function, like this. But the fact that you're working with a scalar function means that by default, most likely you're going to be writing something in terms of x, y, and z. And unless the surface that you're working with, like this one, conveniently has a coordinate system that you already know that allows you to express this in terms of just two coordinates, this is probably where you're going to be stuck with. You're going to be stuck with this function of three different input variables, and you want to get down to two. And once you end up writing out this equation, it's like, well, where do you go from there, right? How can you somehow use this to be able to parameterize whatever your surface is? And it's at this point where I want to say, okay, well, let's maybe pivot and not think of expressing a surface like this. Not thinking of expressing a surface in terms of, most generally, a scalar function. Okay? Now, to understand why we're going to be expressing a surface with the type of function that we are, I actually want to go back to a picture that we've already seen much earlier in the video series. This is a picture that we encountered before we even looked at surface integrals at all, before we were in a previous section. And this might look a little bit familiar. Maybe we weren't just integrating or we weren't integrating over entire surfaces, but we were integrating over a specific path, a specific curve. And if the integral over this path was considered a line integral, right? So with the line integral, let's think back to our step one with how did we, what was the first thing that we did when constructing a line integral? Because really what we have right here is a 1D domain in a 3D space. Now, what we're going to be working with is just a 2D domain in a 3D space, right? So hopefully there are some similarities that we can pull from the line integral case. Now, if you remember, the first thing that we did with a line integral was we came up with a way to model a line integral, which was through a parameterization, right? And we said that a parameterization was, or could have been represented by a vector function, r of u, right? Where u right here was the single parameter that as u varied from the starting u value to the ending u value, that took us from the starting point on this curve all the way to the ending point on this curve. So we could represent this curve by a single parameter u, and the overall parameterization was a vector function. Right? Now here's how we're going to connect the dots going from a line integral to a surface integral. Let's just change our path now so that let's not just change our path, but let's maybe extend this path. Maybe my path is kind of traversing across R3 right now, but let me do something where I maybe do something like this, and I start to draw in these dashed lines right here. And hopefully you can see that with these dashed lines, maybe I started with just a single path, but with the addition of these dashed lines, I've now formed some wavy type of surface that is kind of, it looks almost like it's flowing through my three-dimensional space. And if this is my surface now, which would be this line connected to here, connected to here, connected to here, then if we know that to go across this line, going from here to here, that can be parameterized by a single variable. Then if we're just adding kind of a second variable, now we're going from a line to a surface, you can imagine the only thing that would change in our parameterization is that we go from 1 to 2 different variables. And here's where we're going to start to connect the dots, okay? So for a surface integral, the first approach for modeling our surface is to not use a scalar function, but rather to look at this picture here where our position vector r is no longer just a function of u, but it is a function of u and a second coordinate, v, because now we're working with a surface, okay? Now, the thing that we should ask ourselves is, well, what do we call this type of function right here? R of u comma v. Well, if u and v are two different inputs right here, then we would say that if it has two inputs, then the domain that we're working with for this function is R2. And then if once provided a u and a v value, we end up getting some vector in 3D space, then R takes a u comma v pair and it sends it to an R3 codomain like this. So we can ask ourselves, what type of function has this type of form right here, right? And this type of function that can be thought of as a specific instance as a function that goes from Rm into Rn, right? Where now m and n are different. So it turns out that for these surfaces, these embedded surfaces that we have here, if what we're doing is performing a line integral, the way that we parameterize that is through a vector function. When working with a surface integral, the way that we parameterize that is through a vector field. Okay. So by using a vector field, that is the mathematical way of modeling this embedded surface. That's going to be kind of our starting point. Okay. So hopefully that makes sense, that's going to be what our first step is. We want to use a vector field to model our embedded surface. Now the next question is to ask, okay, well sure, let's say that we're going to use a vector field to model whatever our embedded surface is. What are the conditions that get imposed on this vector field right here, right? Like this function right here needed to have, when we worked with the parameterization of just a line, which is a vector function, that function needed to satisfy certain convenient properties, right? Like it needed to, I think, be at least once differentiable, continuous, and there were certain specific properties that it needed to uphold. So that's going to be the first question that we ask here, is with this vector field, what does that function need to satisfy? Okay. So I'm going to erase the board, and then that's going to be kind of the question that we dive into next. Okay, so what we have written here on the board is we have this sentence that just summarizes what we've established so far, which is to say that if we have an embedded surface, or a surface embedded within R3, then it can be parameterized by a vector field R, which has a domain of R2 and a codomain of R3. I realized there were a lot of R's in that as I was reading that, but hopefully that makes sense, right? Now, what we want to do next is to say, well, what sort of conditions need to be imposed on this parameterization vector field right here? So just coming up with the fact that we can use a vector field to parameterize a surface, we were able to draw from our knowledge of line integrals to do that. But it's this next step where things are going to be a little bit new. We won't be able to draw from our knowledge of line integrals simply because we no longer have R as a domain, but we have R2 as our domain. And we'll see what I mean in a second. Now, to express the general property that we want this parameterization vector field to have, I drew out kind of just the standard R2 surface right here. And then I'm now drawing out a surface that, let's say this sort of flowing surface is embedded in R3. And maybe let me call this surface S. Right here, okay? To understand the property that we want this vector field to have, let's start with this picture right here, where R2 could be parameterized in a number of different ways, but the most common way to parameterize R2 is with the X and Y coordinates, the Cartesian coordinate system, right? And what I drew here with these two arrows are meant to be the directions that indicate a change in each of these two variables right here. So what I mean specifically is that this arrow right here describes a positive change in the X direction, which is going to the right. And then this vertical arrow right here represents a positive change in the Y direction. And in this specific instance, the change in X is perpendicular or orthogonal to a change in Y. But the more general property, the basic idea that we're trying to get, is that the direction that's associated with the change in X, meaning the left and right direction, that inherent direction is just different than the direction associated with the change in Y, which is the up and down direction. More generally, we're trying to say that the directions that denote the change in each of these variables are different. And we want that same property to be contained within our parameterization vector field on an arbitrary surface S, like this. We want the direction that is associated with the change in U to be different than the direction associated with a change in V. However these two coordinates are defined. They don't need to be perpendicular, but they cannot be parallel or anti-parallel. It's kind of the main point. Okay. So hopefully that makes sense. That is the property, that the general idea that we're trying to have our parameterization vector field satisfy. Now the question is, well, how do we do that, right? And the way that we can do that, or in other words, the way that we can impose these two unique directions is to actually go back to our knowledge of linear algebra, where we asked a bunch of different questions, but one of the questions we asked was, well, can we form a basis on our vector space right here? And we saw that in the case of R2, maybe these arrows right here don't just denote the change along X and the change in Y, but they could actually denote basis vectors. Specifically, this could be the I hat basis vector, and this could be the J hat basis vector. right? In other words, we could use basis vectors to help us ensure that that property is satisfied. That as you move along I hat, you're not moving along j hat and vice versa. So that's going to be kind of what we want to do here with our more general embedded surface, is we want to see if we can come up with a quote unquote basis for the surface that we have right here. Okay. And then the question is, well, just how do we do that? Now, if we have a parameterization vector field R of UV, which I can write like this, then what that does is that says for a given set of UV pairs, or a given set of U and a given set of V, it will spit out a position vector from the origin to any point along the surface, right? So what I could do is I could say, maybe let's not just look at this vector V though, but let's look at an incremental change in our vector R right here. So let's not just look at R, but let's look at maybe an incremental change delta R like this and see what does a incremental change in R correspond to. Well, by chain rule, we know that it will have a partial derivative of partial R partial U delta U like this. And then we're going to also have another term, partial R partial V delta V like this. And then of course you could have some higher order terms potentially as well. So some terms that contain both delta U and delta V and some combination of them, right? But this is what we would get if we incrementally change our position vector. We move a small amount in along this surface right here. Okay. Now, just looking at this, we can ask ourselves, well, let's look at the two vectors that we see here on the right-hand side of the equation. I'll underline them. This would be our first one, and this would be our second one. This first quantity right here describes how you can move along this surface, how your position changes along the surface as you change your value of U. So maybe the change along the surface along the U direction, meaning this arrow right here, could be represented by partial R partial U. And then the same thing for this arrow that's pointing more downwards right here. That's represented by how you move along the surface as your position changes as you change your value of V. So if this is partial R partial U, then this vector down here would be partial R partial V. So we saw just from considering a small incremental change in our position along the surface, we were able to come up with two tangent vectors that describe moving as you change U and moving as you change V. What we want to ultimately do, though, is we want to really connect this to linear algebra, which is to say, do these vectors ultimately form a basis on this space right here? Kind of like how the I hat and j hat vectors actually form a basis on the overall vector space. Now, it turns out that there is a certain condition that needs to be satisfied in order for these two tangent vectors that we have right here, these underlined vectors, to form a basis. And it's a certain type of parameterization. It's the type of parameterization that we're going to work with. Ultimately, if we wanted to ask ourselves what properties does this vector field need to satisfy right here, this next definition that we're going to write on the board is going to explicitly answer that question. Okay, so we now kind of get to the official answer to the question of what properties does a parameterization vector field R of UV need to have in order to accurately parameterize a given embedded surface. And it turns out that that parameterization needs to be considered a regular parameterization. So let's go through this definition together. it says here that a parameterization vector field R of uv is considered a regular one if for all values of u and v, this property is satisfied, where the two tangent vectors that we looked at in the previous whiteboard, partial r partial u and partial r partial v, if you were to take the cross product between those two vectors, you do not get the zero vector. Okay. Now, the reason why I spent all that time going through the previous whiteboard is because I could have just, to answer the question of what properties does R of uv need, I could have just written this up here and then we could have just memorized this definition, but it's not the most intuitive one if you don't have kind of the background context, right? And we talked about in the last whiteboard how we would ideally want these two vectors defined on the surface S to effectively form a basis on that surface S. And it is with this definition of being a regular parameterization that we're able to do that, to effectively form a basis on your surface. Now, going back to linear algebra, we're using these words like basis. If we have a set of vectors that form a basis on an overall vector space, then they need to satisfy two properties. And what we're going to do with this definition is we just want to show that with this definition for a regular parameterization, it also satisfies the same two properties that are needed in the definition of a set of basis vectors. Okay. So what are those two properties? What do a set of basis vectors need to satisfy? Well, the first is that the set of basis vectors would need to span the entire space. So span, which in this case, we're just working with sort of this finite surface S. So we're just going to say they need to span the surface S. That would be the first requirement. And the second is that our set of quote-unquote basis vectors need to be linearly independent. Linearly independent, okay? So let's see that with a regular parameterization that this definition, or that both of these properties for these two vectors right here, let's see that those are satisfied. So for the first property, that our vectors partial r partial u and partial r partial v, we want to see that they span the entire embedded surface that we would like to integrate over. And this comes from this ending part of the definition. Maybe I'll stand over here. It comes from the ending part of the definition right here, where if our parameterization vector field R of u comma v is defined inherently for all values of u and v, and let's do this here. Let's say that we have our, whatever our surface looks like, S, like this. If we were to consider all values of u and v that make up this surface right here, the fact that R itself is defined for all the values along this surface means that then you could compute these two vectors for everywhere along this surface right here. Okay. In other words, if you were to take any linear combination of, so if you were to take any, maybe like A times partial R partial U plus B times partial R partial V, because R itself is defined for all values of U and V, then any linear combination of these two vectors right here could reach anywhere on this surface. That is just another way of saying that the span of these two vectors right here span the entire surface S. So it's kind of this ending part of the definition that guarantees that that the two vectors in question span the surface. So we can put a little check mark on this first one, okay? Now for the second condition, we want our two vectors, our two partial derivative vectors, to be linearly independent to each other. Now, there's a definition for what it means for vectors to be linearly independent that gets discussed in linear algebra, but hopefully we remember that if we're just looking at a set of two vectors in question, In other words, if our set of vectors is simply the two tangent vectors partial r, partial u, and partial r, partial v, then the only way that they're going to be linearly dependent is if they are scaled versions of one another. In other words, the only way that these are not linearly independent, and the only way we don't put a check mark here, is if these are parallel or anti-parallel to each other. And it's this, at this point, it's this part of the regular parameterization definition that ensures that our tangent vectors are not parallel nor anti-parallel to each other. So let's make sure we understand why this condition guarantees that they're not parallel or anti-parallel. So with the cross product, if I were to just write out what the cross product is here, and maybe let me do this down here. If I were to take partial r, partial u, and a cross product with partial r, partial v, the way that I could express the result is we take the magnitude of the first vector, so we take the magnitude of partial r, partial u, times the magnitude of the second vector, so partial r, partial v, times the sine of the angle between them, and then I can have a little n hat factor at the end. And again, that's just because the cross product takes two vectors as an input and spits a resulting vector that is perpendicular to both of the input vectors as the output, okay? Now, let's ask ourselves, what is the only way that this quantity is going to be zero? Because in the general case, we can assume that these derivative vectors are non-zero. Maybe for very specific directions, these vectors go to zero. But in the general case, this is non-zero and this is non-zero. So the only way that this overall cross product in the general case will go to zero is if theta is itself 0 or pi. And again, theta describes the angle between these two vectors right here. So if the angle between these two vectors is 0, that is the case where these two vectors are parallel to each other, if they're pointing in the same direction. Then we'd have the magnitude of the first times the magnitude of the second times sine of 0, and that would give us 0, meaning that they're parallel and hence linearly dependent. The other case is when theta is equal to pi. And when the angle between these two is pi, that's 180 degrees. That means if one's pointing in this direction, the other is completely anti-parallel to it, pointing in the opposite direction. So then sine of pi would also go to 0 as well. Those are the only two cases, the cases where our two vectors are parallel to each other, and then the case where they are anti-parallel to each other. That's the only way that we're going to get 0 for the resulting cross product. But with the regular parameterization, we require that the cross product is not 0. And if it's not 0, that means theta, therefore, is not 0 or pi. So maybe let's write that out. We could say for a regular parameterization, it's a lot of letters, for a regular parameterization, if the cross product is not 0, then therefore theta is not equal to 0 or pi, like this. Okay? And if theta is not 0 or pi, that guarantees that this first tangent vector needs to point at some angle relative to the second one. And as long as they're not parallel or anti-parallel, they need to be linearly independent. Okay? Hopefully we can sort of track the logic there, right? And understand that they have to point in different directions. So for a set of two vectors, that is good enough to ensure that those two vectors are linearly independent. Okay? So then I guess overall, just summarizing what we've just said, because these two vectors, these two tangent vectors, both span the surface, whatever our embedded surface is, and they are linearly independent, we can effectively think of them as forming a basis on the surface. And therefore, as long as our parameterization is a regular parameterization, which can be easily checked by this condition right here, we have a good parameterization for whatever embedded surfaces that we're working with. Okay. So a lot of little arguments, right? But I hope if we go one by one through those arguments, those make sense. Now, the final thing that I want to do is I want to erase this and to say, okay, sure, we've kind of built up the fact that our embedded surface needs to get parameterized by a vector field, and that parameterization needs to be regular. So how can we now use that to start setting up embedded surface integrals? And we'll use that to finish out the video. Okay, so kind of to put everything together that we have so far, and this is where we're going to connect a bunch of dots that if we haven't connected them before, hopefully we can connect them now. So right now what we have is sort of this picture where we have this embedded surface, and this surface is embedded in maybe like a 3D space, but we'll call this S right here. And let's just say that we've achieved the things that we've wanted to develop so far. So we have a surface, we've come up with a parameterization vector field for it, R of uv, and not only do we have a parameterization, but it is a regular parameterization. Okay, so the tangent vectors, the first order partial derivatives of R, are pointing in different directions from each other. Okay, so let's say we have that. And now let's take the next step, which is to say, well, whatever this surface is here, it has some area. And let's try to figure out how we can calculate the area of this surface. And the area of the surface, I'll write the area, and this part should hopefully be pretty intuitive. That's just the integral of all of the ds elements. So if this is a surface S, you add up all of the ds elements over S, and you get the total area, right? So that makes sense, but it's the way in which we compute this that is not so trivial. And in order to understand why, we need to introduce another sort of figure in the picture. And this difference might initially seem subtle, but it's going to be very important. So hopefully you can stick with me on this. This surface right here, it's parameterized by u and v, and which says that if we were to go across this surface, u is going to take on some range of values. It'll have some starting and ending value, and so will v. V will also take on its own range of values. And if you combine the range of u values with the range of v values, you would get an overall domain for all of the possible values of u and v together. If you were to plot all of the possible values of u and v that make up this surface S, you could do so on a 2D plane, where this 2D plane is not an xy plane, but it's just a uv plane. So this is u and this is v, like this. Maybe changing in u corresponds to changing in this direction on this flowing piece of paper, right? So maybe u changes along this direction, like this, and then maybe v changes something like along that direction, right? What you could do is, if you were to plot out all the possible pairs of u and v together, you could do that in a uv plane, and maybe u goes from 0, some starting value of u, so like 0 to some final value of u, and then maybe v goes from 0 to some final value of v. And then together, you might get this overall just rectangle, where the rectangle represents all the possible pairs of u comma v that go into making this surface. Hopefully we see that S is fundamentally different than, we're not looking at the exact same surface here, right? This surface is embedded in R3, whereas this is just a 2D surface in the UV plane. Okay, so they're different quantities, and it's this quantity here that I'm going to give the name D for the domain of all possible UV pairs. Now we might be thinking back to previous videos where we were saying if we wanted to integrate over some subset of R2, we denoted that with the letter D. Is that the same thing that we're doing here? And the answer is actually yes. It turns out that what we've been doing up until this point, when we looked at the subset, when we looked at subsets of R2, the subset itself, the thing that we wanted to integrate over, was all of the possible values of U and V. So in other words, the surface we were integrating over was in fact this surface. It's only when we start to work with embedded surfaces where now the domain of all possible UV pairs is fundamentally different than the surface itself. They are distinct quantities. It just hasn't been that way because we've always worked under the assumption that we were working on a subset of R2, okay? So that's kind of this subtle difference, is that we're going to want to distinguish all the possible UV pairs plotted in this 2D plane with the actual embedded surface up here, okay? Now here's why we want to make this distinction. We might be saying, why? Okay, sure, maybe there's a distinction between the embedded surface and the domain of these inputs right here. Why are we making a big deal out of this? And here's the reason why. We might think that if we wanted to compute the area of this embedded surface right here, we would do this, but we might think the way in which we perform this integral right here is we integrate over all possible values of UV, and this is going to seem sensical too, right? We might think that we want to integrate over all the possible values of U and V. That's denoted by D, so we might think that we want to integrate over D, and we integrate with respect to U and V, like this. And we might think that by performing this integral, that is the way in which we compute the area of this embedded surface right here. But it turns out that this is false. All right. And it's this subtle thing, but it is true that this quantity right here is not equal to this quantity. Now, the first thing that we should be asking ourselves is, well, why, right? It seems like it makes so much sense. U and V are the coordinates that make up this surface right here. Let's just take their range of values and integrate over them, and that should give us the total area, right? So how come it doesn't? And the reason why it doesn't is because if we were to take an incremental area in the embedded surface, delta S, that is different than an incremental area in the domain of these values, D. These quantities here are not the same. So hopefully you can see why I'm trying to stress the distinction between the domain of input values and the embedded surface itself. Because when we take these incremental areas, then we don't get the same thing, and we want to understand why. Okay. And let me actually just start by writing out, let's do this. Let's write, same thing, but let's write that a little change in an incremental area in D is not the same as an incremental area in S. And let's just start by saying, okay, well, how do we compute an incremental area in D and in S? And we'll start with D, because that's kind of the more familiar picture that we've been working with up until this point. We've been integrating a lot of domains D. So when written in the UV plane, if D takes on this form right here, then an incremental area might look something like this. And obviously I'm kind of blowing it up so we can see, but you can imagine if you took a little square chunk out of the overall domain, this is what you would get. Where maybe you take these 4 points right here, and then you just ask, what's the width of this square or rectangular domain? And that's just the width times the height, right? It's going to have a width of delta U, and it's going to have a height of delta V. Right? And hopefully that makes sense. So delta D is simply going to be the product of delta U times delta V. So on this left-hand side here, I simply have delta U times delta V. Okay. That's how we can compute incremental area in this flat 2D domain right here. Now the next question is to say, well, what is this, the corresponding, I guess, incremental change in the embedded surface right here? And I'll try to draw this as best as I can. And it might look something like that, right? And again, I know this area is way bigger than this tiny incremental area that we usually denote with delta, but this is just to prove a point right here. Okay. So if we are given a regular parameterization of this surface, as we move along maybe the u direction, let's see what does that correspond to moving along the u direction. Well, we need to move along just the tangent vector, right? So, and maybe let me zoom in on this square that we have right here, and I'll do my best to draw it down here. We have something that looks like this. Something that maybe looks like this, right? If we were to move along the u direction, what that would correspond to is moving along the tangent vector partial r partial u times this increment delta u, right? And then what about the v direction, moving along this direction? Well, that's just moving along the tangent vector partial r partial v, but we're just moving along it a small amount. We're moving along it by an increment delta v. Okay. So because these quantities right here are different that make up this small area where this overall area here is delta s, this is delta d right here, hopefully you can see why we don't just get delta u times delta v. Because there's more stuff that gets contained within it, right? In order to specify those directions, we needed these partial derivative vectors right here. Now notice that there's also an additional problem where we can say, all right, well if these are the directions, can we just write partial r partial u delta, maybe let me put a question mark here, but partial r partial u delta u times partial r partial v delta v. Can we do that? And the answer is actually no, right? And the reason why is because these partial derivatives are vector quantities. These were like the quote-unquote basis vectors defined on our embedded surface. And one thing that we cannot do is we cannot multiply two vectors together. If we want to multiply these two vectors, we need to perform a vector product, but we can't just do straight vector multiplication. By elements of a vector space, you can only do vector addition and scalar multiplication, right? So this right-hand side here actually isn't even mathematically correct. It doesn't even make sense to write this because this involves the multiplication of two vectors. So there's something else that we need to be able to write out to express what this differential or this incremental area delta S is right here. And maybe let's just draw an arrow. That is this thing. Okay. So in order to do this here, these would be like the side lengths of our incremental area delta S. And we now have to go back to properties of vector product quantities, or of vector products, I should say, in order to understand how we can compute this overall area right here. And specifically, because we've been working with a regular parameterization, which involves a cross product, let's go back to our knowledge of the cross product. So over here, this is going to be like a quick cross product recap. If I have A cross B, any two vectors, A cross B, maybe A is this vector, and then B is this vector. What this cross product computes, well, it's a vector. The output of this is a vector. So it's going to have a magnitude and a direction. The magnitude of this vector right here, in other words, if I were to draw the magnitude signs around this, that would simply be the area of this parallelogram right here. Then the direction would be a little n hat vector that is pointing perpendicular to both A and perpendicular to B at the same time. But the point that I'm trying to get across is that if you were to take the magnitude of the cross product, then what you're doing is you're getting the incremental area of this parallelogram formed by A and B. Let's relate that to over here. So if we want to find the incremental area, and these are the two vectors, the way that we find this area then is just by the magnitude of the cross product of these two quantities right here. Okay? So it turns out that delta S itself is the absolute magnitude of partial R, partial U, delta U, and a cross product with this side now, right? Partial R, partial V, delta V. And what you can do is this is a vector times a scalar and a cross product with a vector times a scalar. I can move the scalars out to the front and just leave the vector quantities inside the cross product. So I can rewrite this side over here as partial R, partial U, cross partial R, partial V, and then delta U, delta V, like this. Okay. So hopefully we see now that the reason why an incremental area in the domain D, the reason why that's different than an incremental area in the embedded surface S is because delta U, delta V is what we get for delta D. And on delta S, we get that same factor, but we also get this additional factor, which is the magnitude of these two quote-unquote basis vectors that get used to describe, or these two tangent vectors of the parameterization vector field. Okay. So that's where the difference lies. And that's why we can't just perform this as our integral over the area. But this has been a lot, up until this point, this has been a lot of, this is what we can't do. What can we actually do though, right? Our goal here is to find the area of the embedded surface. And what we did say was that the area is just equal to integrating over S of these small incremental areas, ds. Now that we have an expression for, I guess, well, delta S, let's use that in the actual integral. So this is where we start connecting the dots. To compute the area of this embedded surface, this area right here, that would simply be the integral over S of ds. And what that is equal to is the integral of the magnitude of the cross product, partial R, partial U, cross partial R, partial V, du, dv. And it's at this point where we can put this subscript d right here. Okay. So it's at this point where once we include this factor, the magnitude of this cross product, now we can integrate over all possible values of u and all possible values of v. Okay. And it's this magnitude, it's this conversion factor that lets us relate these two spaces that we have right here. Okay. So this is kind of the first step. This is how we would perform our first, more or less, integral over an embedded surface. Now, just to, I guess, finish out the video, what we've been doing a lot of the times is not just finding the area of our domain, but we've been integrating a scalar function over our domain, right? Where what we would be computing previously might have been, I don't know where I'm standing, it had been the integral of some function f of r over the domain, right? So what would happen if we wanted to integrate a scalar function now over this embedded surface? So let's say like the temperature or the mass density or the whatever, some scalar function is defined at all points on this embedded surface. What we would do is if we wanted to compute the surface integral of f of r ds, like this, what we would need to do is we would need to then integrate over d. be able to express f of r as a function of u and v, right, using our regular parameterization. So f of r gets written in terms of u and v. Then we have the magnitude of this cross product. So of partial r, partial u, cross partial r, partial v, du, dv. And I realize I'm running out of space here too. Du, dv, like this. Okay. So this would be the process for computing embedded surface integrals. And hopefully you see why getting this factor right here is not a trivial process. You really want to go through the logic to make sure you understand where it's coming from. Okay. I think I want to call the video at this point. Just developing the framework to be able to talk about these embedded surfaces and then to be able to come up with this factor, I think is good enough. In the next video, we'll start to do more with embedded surface integrals and computing specific types, very common specific types of surface integrals. So should be good, and hopefully you guys stick around for that next video. So yeah, see you then.